Okay, and we're starting. So, as we all know, your test is tomorrow, and it's going to be pretty much like the practice test that I posted online, so there should be no surprises. Like I said, the only difference is I probably will add a couple bonus problems, maybe with some harder set problems, or counting, which you probably would actually start doing today if everything goes well. If you have questions. I give you the formulas only for the financial math. So you don't have to remember the amortization or the sinking part.
Yeah, can you do that, please? Come on.
Okay, I'll give you the title for the sinking fund and amortization.
Like you'll say this
But
is
of course.
present value and like payment.
No, I'm not going to do that. Like, I'm going to give you the form. Here's the amortization form. You should know what the pieces mean.
Wait, like are they all written in that like?
Wait, are you going to give only those two formulas or like the others?
Huh?
Are you going to give us payment?
Yeah, so you know PMT is
We don't have to divide them from like the actual
say this is
present value formula.
No, you don't have to derive anything. You just need to know how to use the formulas. You need to be able to read a word problem and know, oh, this is the formula I'm supposed to use, and use it. Yeah.
Do we get credit if we like get the answer right, or?
No, I'm grading all your work.
So it's based on process as well?
So if you get like a number wrong here or there, I'll take off a couple points, but if you have the overall idea. Like the only thing where it's like definitely not is like if you choose the completely wrong formula. If something needs amortization and you choose the sinking fund formula, you could do that perfectly. I'm not gonna really give you credit because you chose the wrong thing. Yeah.
Is the level of difficulty same as the practice test that's on Jhevon?
Yeah.
Not very much.
For those kind of like a month is 30 days, some years 365, we don't really practice.
Yeah, you're not gonna have to do any crazy counting like between September 3rd and October 14th or whatever. Yeah, so don't worry about that. So you'll be counting around months.
It wasn't that hard, but I've done all the practice stuff, like the other two practice problems beforehand. So,
Yeah, so it's gonna be here. It's gonna be the whole period. It's gonna be like 8 problems ish, and yeah, bonus points. So it'll look like the practice text, which is different from the practice files, right? So I gave you a couple like files where there are like 20 problems in it. That was just to get you in the groove to do the practice test, so that the shorter test towards the end. That's how long it's going to be. So today, we're going to again take it easy. I mean, we have a test more, so we're not going to do anything too complicated. In fact, the first part of the class is going to be, at least I think, a little bit of fun.
Yeah, so we have problems.
and then like one of the problems I looked hard on here, that's awesome here, but I know I didn't realize that.
So we'll start out with some probability teasers.
Linear programming.
Does anybody else need one?
I had to watch.
Okay, so these are kind of, well, some of these are a bit of unique. Who else needs?
Yeah, just a couple.
So the next big phase that we're going to be talking about in our class is probability. We're going to learn all sorts of things about probability. And we're going to be seeing that being able to count things very efficiently is going to be very important for probability. And a lot of people think they know how to count, but we're not talking about counting like 1, 2, 3, 4. We're talking about counting with sophistication, counting efficiently. And I don't mean, that's not what I mean. Yes, we want to be able to count big things really fast, but we also want to be systematic in our counting. And I guess to illustrate that, I wanted to actually look at some probability problems and see if we could figure them out and see where our probability muscles are and see what we really need to work on. So that's what we do. I thought we'd have a little activity. So I'm not going to teach you how to solve all these problems today, But just to throw some ideas out there, have you thinking about them, and then we'll actually go back to counting, learn how to count, and then revisit probability, and you'll see that with our counting strategies up to scratch, it's actually a lot easier than we thought. Just to give like a fuzzy, some sort of definition here. Let's just make this a little bit fair. What do we think probability is? When you hear the word probability, what do you think? Yeah.
Chance of something occurring.
Chance of something occurring. So this is usually called an event. But what do you mean chances? What is the chance of change? What does that mean? Yeah.
The likelihood that it's going to occur over something else.
The likelihood, but again, what does that mean? Mathematically.
Percentage possibility.
Percentage possibility, that's getting a little more precise. So it's the percentage possibility of something happening. How do you actually calculate that? Yeah.
The amount of times it actually happens divided by n total trials.
Okay, so for finite probability, there's a difference. There's probability where we're looking at infinite sets, but we're talking about finite probability. Yeah, you want to say it's a measure probability. What we call it is a measure of relative frequency. This is the chances of something occurring, and basically what this is, loosely speaking, we will define it. Well, you're going to want to figure out all total number of possibilities. In some situation over the number of ways a particular event can happen. Now we'll write this down a little bit more mathy, but I just want to make sure that we kind of have an idea. And this is the probability of the event. So, for example, if I flip a coin, assuming that the coin is a fair coin, and someone can ask what is the probability of if I flip a coin, it will land with the heads facing up, as opposed to the tails, I can say, well, the total number of possibilities here is that it can either land on heads or tails, so there are two possibilities. And if I'm looking for it to land on heads specifically, that's just one way that that can happen. It would have to land with the head facing up. And so I would take 1, I would divide it by 2, and I would call that the probability. And this is just the kind of percentage chance of actually getting a heads. One thing is that's actually important that we notice though, is that probability is measured on the aggregate.
What does N mean?
Note. What that means is you could flip a coin twice and not get heads half the time. It's possible that you get tails both times. You can flip a coin 5 times and not get heads half the time. Probability is really measured on the aggregate. We have something happening a lot of times. If you were to flip a coin 1,000 times, 10,000 times, 1,000,000 times, that's where when you start to count the number of heads, it starts to go towards that 50%. In the short term, you might not actually hit the probability that you calculate, but it's just telling you, if this were to happen over and over and over again, many times, this is roughly the percentage of times that you will have heads. So yeah, I can flip a coin twice and never get heads. But if I flip a coin 1,000,000 times, about 500,000 of those times I'll see heads over the aggregate. So that's also pretty important. So a probability is not a guarantee, it's a chance, there are risks associated with it. and that's going to be important. So that's kind of the basic idea. So now that you know the idea, let's actually look at some of these guys. So, I know I didn't teach you much about probability, and we only did a smidgen of counting, but I kind of just want to see what you guys will be able to figure out just by us going through these problems, see where your intuition is versus where the actual answers are. So, the first problem on page 1 is a very famous problem called the Monty Hall problem. I always want to say Monty Python. So, Monty Hall was a game show host, very famous way back in the day. I don't think I've ever actually seen any episodes of this, but this was way back in the day. I know of the game show. And this problem actually was published, as you can see here, in around 1975. And that's back when people used to read print media all the time. So whenever a math problem came up in like a magazine or a newspaper or something like that, everyone was talking about it. So the Monty Hall problem was a very famous problem because it was very controversial at the time, and you would have people arguing over it all the time. So here is the problem. If you're on a game show and there are 3 doors, door number 1, and door number 2, and door number 3. Has anyone seen this problem before?
Yeah, it's really good.
You guys, okay, so you guys be quiet. Right? So we're on a game show and there are 3 doors. And so what's happening is you get to pick any door you want. And you will win the prize that's behind the door. So now, here's what's behind the doors. Behind one door, a car, brand new car, the newest. So your dream car is behind one of these doors, and behind the other 2 is a lesser prize. Traditionally, it's a goat. So there are goats behind the other 2 doors. Right? So you can win a goat or you can win a car. Now, some people might want to win the goat, but we're going to assume you actually want the car. Okay? So you pick a door at random on this game show. Okay, pick a door. What door do you want to pick? Door number 1. Okay, so he picks door number 1. So now what Monty Hall does, the game show host, is he shows you another door. He goes over here and he's like, he opens door number 3, and behind door number 3 is a goat. And then he says, do you want to switch your answer? I mean, here's a goat right here. You could have picked a goat. Do you want to switch to door number 2, or do you want to stick to door number 1? And the question is, what is the best choice? Now, this is actually something that has to do with chance, as you can see. You have no idea of knowing what the best choice is a priori, but what you want to basically figure out is on the aggregate. If I were able to make this choice over and over and over again, what choice would actually get me to the car most often, and that's the best choice to make. And we'll talk a little bit more about that. So what do? And it was very controversial. Like, there were a lot of people say, oh, you should, it's not going to matter. Like, if the car wasn't behind door number 1, it's not going to change just because he showed you another door. And some people are like, nah, maybe you should switch because, you know, maybe he's trying to help you out, or maybe whatever. And then there are other people, you know, that get suspicious, you know, door number 1 means something to them. It's the number 1. And so I'm going to stick with door number 1 because, you know, I'm all about being number 1. So what is the best strategy? Any guesses? Someone who's never seen this before. What do you think? What do you think? Should you switch? Yes. Yes, you should switch. It's going to make a difference.
are you calling for a vote?
I'm calling for a vote, yes, that's
Let
what
us
it
vote
says.
if we know the answer.
Yes, don't vote if you know the answer. Do you?
Kevin Spacey though, he's the.
You saw the movie?
Yeah.
Did you guys see the movie?
Yeah.
21, you guys saw that movie? No? You guys should watch that, it's a really awesome movie.
It's one of Kevin Spacey's.
Let's watch it tomorrow.
Let's not go there. Yes, Kevin Spacey is in it. It was long ago. Anyone vote? Yes? No? No. No. Let's not switch. It doesn't make any difference. What are you talking about?
Wait, they don't know that the car is behind the first door, right?
Who?
Whoever's choosing.
Well, the game show host knows the answer, but you as a contestant, you
Don't know, right?
You're a guess, yeah. You are randomly guessing.
Yeah, so they shouldn't switch.
So yes. Apparently nobody thinks that. No. I have 3 brave souls willing to cast a vote. And the answer is yes. It makes sense to switch your choice. You will win the car more often. In fact, you are twice as likely to win the car if you make the switch. You double your chances by making the switch. Why is that? Turns out you have a 2/3 chance of winning if you switch, and you only have a 1/3 chance of winning if you don't. Okay.
But you already know that the third door has to go, right? So what's the point of switching?
We'll talk about it later. Don't worry, just think about that. Let that sink in for a little bit. Now, there are 2 other problems here that mathematically they're equivalent to the Monty Hall problem. I just put them down here for historic reasons. Another very famous one is the 3 prisoners problem. So here's how that problem goes. You have 3 prisoners, A, B, and C, and they're all sentenced to death. And, to save on electricity or whatever, the government decides, I'm not going to execute everyone. We're going to randomly pardon some people. And so what happens is the governor says, you know what, we're going to pardon one of these guys at random, we're going to execute the other 2. And the warden actually knows who's going to get executed from who doesn't. So as you see here, what happens is, who went to the warden? I don't think it matters, but yeah. Prisoner A goes to the warden and says, please, let me know, am I going to be executed? Tell me what's going to happen tomorrow so that I can sleep soundly tonight. Please tell me who's going to live, who's going to die. And the warden says the following. The warden tells him that,
A and B.
where is it?
A and B.
Yeah, he needs to be executed.
No. The warden tells A that B is to be executed.
Where am I? So prisoner A begs the warden, let him know the identity of one of the others who's going to be executed. And he says, if B is to be pardoned, give me C's name. If C is to be pardoned, give me B's name. And if I'm to be pardoned, flip a coin and decide whether to name B or C. So that was the game. Sometimes it's phrased differently from that. Sometimes it goes, the warden says, well, I can't tell you what happens to your own fate, but I can tell you who's going to serve, one of the people who's going to die. And essentially you end up mathematically with the same situation. So the warden tells A that B is going to be executed. B is one of the ones who died. So prisoner A comes to the warden and he says, you know what? Prisoner B is one of the people who's going to die tomorrow. And so what happens is prisoner A now feels kind of relieved. He's like, okay, so I'm definitely not one of the ones, I'm probably not one of the ones dying tomorrow. Before there was a 1 in 3 chance of me dying, now it's a 50-50. Now it's between me and prisoner C, right? So he feels great. He goes and tells prisoner C, hey, don't worry about it, because I know B is one of the ones that is going to die tomorrow. So we're probably, it's a 50-50 chance. It's a coin toss. So let's, we can sleep a little bit more sound tonight, but B is definitely going to die. And so C is also happy to hear the news because now he thinks that his chances of surviving have actually doubled. And in fact, A, the guy who asked the warden about the fate of the prisoners, his chances are actually the same. And the question here is, who is correct? And it turns out that prisoner C is correct. The guy who goes to ask the warden, his chances of surviving have not actually changed. He's happy for zero reason, no reason for him to be happy. He still has a 1/3 chance of surviving. However, prisoner C, the guy who was just in his cell minding his own business, his chances of surviving doubles by knowing that B is going to be executed. And that's similar to this. We had the 3 prisoners, only one is going to survive, and the switching idea actually helps us figure out who is going to survive with what probability. And there's another problem here. I don't want to get into that. But these problems are a little bit more sophisticated. We are going to learn how to solve problems like this, but I just wanted to throw that out there for traditional reasons. Let's look more like at problems that I'll probably give you towards the beginning of probability. This one I think is really interesting. So problem 4. A couple has 2 children. Okay? So this is what we know so far. You have a couple, they have 2 children. What is the probability that the children are both girls? Assume that the probability of having a boy or a girl is the same, 50-50. 50% chance either or. What's the probability that this couple has 2 girls? You know they have 2 children, and A, so this is for problem 4. Probability that they have 2 girls. What do you think? If the chances of having a boy or a girl are assumed to be the same. Yeah?
1/2 times 1/2.
1/2 times 1/2. Okay. Other guesses? Are we all just shy?
I think that's right.
Yeah, you agree. That's actually right. You guys have seen some probability before, all right. Okay, so now let's make this a little bit more interesting. If you know one of the children is a girl, what is the probability that the other one's a girl? Does that actually change the situation? Yeah?
Be 1/2 times 1/3.
1/2 times 1/3. So you're saying that's 1/6 is the probability? Yeah?
I would just say 1/2 because each child is independent of the last.
Yeah, like you know one is a girl, so the probability of the second one being a girl, now it's like, oh, you just have to choose boy or girl, right? So 2 chances, 1 out of 2, I mean you're going to be a boy or a girl, assuming that we only have 2. And yeah, both of you are incorrect.
1/2
Chance is a third.
Why? What's the third gender?
I never said there was a third gender. We're assuming there's boy and girl.
So,
Chances of third.
why?
Okay. Try this other situation. There's a genetic explanation. No, there's a math explanation. Okay, so what if you know that the older girl, and this is, and pay attention now, the older girl's name is Freuda. Okay? What is the probability that the other is a girl? Freuda, kind of like Friday.
Florida? Florida.
What do you think?
What does the name of somebody have to do with the chances of their gender? It's still 1/3.
still 1/3.
Like you guys are all wrong.
Yeah, wait, can you explain the
Yeah,
one
can you explain?
It's a half.
What? That's why they're called teasers.
It's a half.
This cannot be true. You make no sense.
Those are the chances. The probabilities.
Yes. Exactly.
When it's referring to the older girl Freuda, is that referring to these?
We need
Her
a
name's
science
Freuda.
teacher up in here.
Just
Wait, is it because you don't know if
Wait.
it's the older or the younger one?
What?
And you're saying that the older girl, so doesn't that mean that the younger one is sisters? There's a 100% chance that it's 2 girls.
No.
It's a half, right?
These are all different questions in different
Wait,
situations.
is it
Oh.
So-
you know that
So it's like, if you know that have 2 children, what's the probability it's 2 girls? It's a quarter. And then, okay, start over. If you know they have 2 children, what's the probability if someone tells you one is a girl that the other one is also a girl? That's a third.
Why is that a 100?
And because we counted, just like I showed you the relative frequency. We're gonna talk about it. Like the point of having a teaser is for me to just mess with you guys. Like that's the whole point of this whole exercise. Okay, if you know they have 2 children and someone tells you the girl's name is Freuda, the probability is now a half. And this is illustrating an important point that we're going to bring up in probability, that knowledge of the situation actually changes the chances. The more you know about something, the chances will change. Now the question is, why do they change in this way specifically? Here's another situation. One child is a girl born on Monday. Let's say you know what day one of the girls were born. What is the probability the other is a girl?
1/5.
No, I'm gonna
1/1. Yeah.
Oh, you're trying to look at a pattern? Yeah, it's 4, 3, 2.
No.
It's
I'm
gonna
say
be
1 out of
1.
7 because there's 7 days in a
1/1.
week.
I think it goes back to a third.
Half.
1/16.
We're just throwing out
No, I was-
numbers.
I
Do you guys
was-
actually have a reason?
final answer is a third.
7.
1 6.
going to pattern.
13 over 27.
What?
That is true. It's true. That's
I'm
13
gonna
over
replay that laugh on the camera.
27. We are going to calculate this. I am going to teach you how to do these problems. Okay. 7 times 2 is just... Yeah, that's the trap you don't want to get in. You're just now just throwing out a bunch of numbers here that make sense to you, and then you're trying to combine them.
Oh, I
I
get
never
that.
even noticed you guys.
That was kind of.
You know, there's a trap to that. So in the first case, you just like we took a half times a half, and so we're thinking, oh, a half. Maybe just multiply them. Why would you multiply? That's what we want to know. Why would you divide? Why would you do something in a probability problem? Let's move on to the next problem.
You always watch this video.
You have 4 playing cards, right? Like in a deck of cards. 2 are black and 2 are red. You shuffle them. You pick 2 at random without knowing the color. What is the probability that you actually picked the same colored cards? Now, this means you either pick 2 reds or 2 black. What do you think?
2/3. 1/3. I think 1/2.
Yeah, I think 1/3.
1/16.
Oh, wait,
No, 1/3. It would be 2 or 4 times 2 or
Just
4.
2 red, 2 black. Any 2 reds, any 2 blacks. We're just really focusing on the color here.
2/3.
1/2.
I'm saying the 1/3.
I think 1/3.
1/2.
Oh no, 1/4. I think 1/4 actually.
Yeah. There's 4 different.
I say 1/4. I think it's 1/4.
Quarter you get.
Give me the thread.
What a 4, 4.
32 over 27.
42 over 193.
It's 1/4. What?
No.
I thought it was
So
1/4.
1 in 3 chance that you'll actually pick both of the same color.
Oh, there's 2 successes.
I thought it was like 2
No,
over
this is
4
that
times
makes
2 over 4.
sense.
That's
This is
the same.
like
Okay.
black, red, red,
How do you know it makes
Oh,
sense? You
no,
don't
I-
even know
no,
what
I
I'm doing
understand.
to get these numbers.
like black, red, red.
This was the same as B.
Wait, is there actually like a method?
That's why I
Is
said
it the same as the girl problem?
I thought it was the same like idea behind it. That's why I said 1/3.
Well, the color here, it says you can either have 2 blacks or 2 reds. I mean, the girl problem is just 2 girls.
So I simplified that's what I always just assumed it was 1/3.
Okay, let's, this time we have 4 coins. And throw them on a table, random. Probability that 2 of them show heads.
1, 8.
Was probably that 2 of them will show heads. Guesses?
Why do we even know? Who sits down and like, damn, what's the probability of this turning to heads?
Yeah.
Say
1/8.
I mean, isn't that kind of like having the 2 girls?
No,
No?
because there's only 2 of them. This one is 4.
Wait, isn't that like that?
That's what I think.
Yeah.
1/4. 1/3.
I'm going to fun
He's gonna say 1/3.
1/4.
3 eighths.
Okay, I got
Oh, yeah, it's not
eight,
eight.
right?
It's not.
No, I laugh like that. It's like,
How many people do you need in a room so that it's likely that 2 people have the same birthday?
okay, this is like.
365 times 2.
You remember the birthday? This is called the birthday problem. It's also very famous. We are also going to solve it. I'll probably solve this in several ways.
There's definitely.
1/365.
It's like 30 minutes.
Wait, this cannot be possible because like people were born in different years too.
We were ever taught like the reason.
How many people must be in a room for at least 2 for it to be likely? Meaning there's more than a 50% chance. 2 have the same birthday.
2 billion.
It's either thinking it's 42 or
I mean, what are the chances?
Where is that number?
Now this is a little bit
From the
more
Yeah.
involved in counting, but I'll tell you the
What school y'all
answer.
went to?
It's actually 23.
So, oh. So 18,000.
And in this class, we have 27. So you know what? If I were to bet money, if I had to, someone had a gun to my head. The chances are, at this point with 23, it's about like 51%. So it's very bare. But yeah, I think 2 of you have the same birthday.
Okay, let's find
Yo,
out.
July 7th.
June 24.
August 15.
Oh, we're close.
23. You take groups of 23 people randomly 51% of the time.
Oh,
If you
wait,
do that many, many times, 51% of the time, 2 of them will have the same birthday.
When's
It's a
your
little
birthday?
bit more than, maybe it's like 50.5% or
When's his birthday?
51%, something like that.
We could throw him a math party.
Now the last 2, these are actually kind of tough. At a certain intersection, every minute an average of 25 cars
You could
pass.
guess and that's his kid.
What is the probability that exactly 25 cars will pass through the intersection in the next minute? That one's kind of tough. I may or may not show you how to solve that one, but if you're curious, it's 9%.
9%.
9%. So if you're standing at this intersection and you're just counting the number of cars that pass, and you realize that, you know what, every time every minute, or on average 25 cars will pass through this intersection. What are the chances that you will see exactly 25 cars pass in the next minute?
Who
It's
stands
9%.
and counts cars in the intersection?
Yeah. That one, I think you can figure out using something called a poisson, or random variable. Poisson. Okay,
So it's not like I have anything.
now this last one, sometimes it's actually told in a different way. But two bankers arrive on a platform of a train station at random time between 5 and 6. So these guys, they just have a schedule where sometime between 5 and 6, they're going to get off at a certain train station. At that point, whenever they get off, they stay for exactly 5 minutes and then they leave the train station. They probably get on another train, which is within 5 minutes away. What are the chances that on some particular day, these two guys are actually going to meet on the platform?
One out of 144.
23 out of 144 is the answer. And that one, unfortunately, we're never going to learn how to solve in this class because you need calculus to actually answer that problem. There comes a point where probability gets complicated
Wait, what
enough
was
to
it?
require
20?
calculus. We don't know any calculus
Oh,
yet.
okay.
But all the other problems on this sheet, we can actually figure out how to do that in this class. Let's look at the boy-girl problem. Let's actually take away some of the mystery there.
Boy, girl.
Yeah, the problem
Oh, the
4.
I thought it was just girl, girl.
So, now, when you want to solve a probability problem, it's going to depend on how you want to set it up. And so, in problem 4, so we have a couple has 2 children. Now, I'm going to look at this in a particular way here. Let me ask you this. Now, this was a question that I've asked before, but it's going to actually put you on to the answer. Is it better to think of the children as a set or a tuple? Would you think that this couple has a set of children? Or a tuple of children? Now, I'm going to be clear why we want to think in this way so that we don't get surprised by these numbers. But what do you think? Yeah.
I think it depends on the question, because if it's asking about like the age of who's the first, like it's a second, it would have to be a tuple. But if you're just asking about the kids in general, then it would be a set, it doesn't matter what they do.
Are you sure?
Sets my brain.
Well, what would a set tell us? Let's say we have 2 girls. How would you represent that in a set? GG. That's a problem, isn't it?
Yeah, you can.
It's a problem. The set is going to be like, okay, it's G. It's not really a good way to think about it. It's actually better to think of it as a tuple. Now, we can think of a tuple. And so now, what would we have to worry about? Well, if I can think of the children as being in 2 coordinates, what are the possibilities here?
Girl, girl.
Well, we could have 2 girls.
Girl, boy.
We could have a girl, then a boy. They could have had a boy, then a girl. Or they could have had 2 boys. So once I think of it as a tuple, it now becomes evident that there are 4 total possibilities. So this is for problem A. There are 4 total possibilities. Now, once you know there are 4 total possibilities, what are the chances that both are girls?
1, 4.
In one of those possibilities, we have 2 girls. Let's look at the other situation. We know that one is a girl. What is the probability that the other one is a girl? So in part B, what actually happened? So we look at this problem, we consider, does it make sense to think in terms of sets and tuples for this problem? Makes sense to think in tuples. What would the tuples look like? They would look like this. How many of them there are? 4 of them. That's where the counting is going to come in. Because sometimes it's not going to be this small. can have many, many, many. You want to know how to count this efficient. In B, what are the total possibilities? We're told what? We're told one is a girl, which does what? It excludes this from a possibility. So what we have now is GG, GB, or BG. Now there are 3 total possibilities. In how many of those possibilities do we have what we want?
1.
Again, 1. That's why the probability in this case was 1 out of 3. Because there were 4 total possibilities. Now, what about the other one? In C, what are we told in C? The total, we're told that the older girl is, her name is Freuda. What are the total possibilities in that situation? There are 2 total possibilities. How do I know that there are 2 total possibilities? Well, we're told that the older child is a girl, which means G has to be in the first position, which means it eliminates this and that from the total possibilities. Now there are only 2 possibilities, and how many of those have what we want? Well, only one of them. So probably here is going to be a half. Now you go into the situation where, now what I'm doing here, this is called enumerating. This is when you literally go through and painstakingly list all possibilities. There are going to be ways to avoid that, which I'll be teaching you in the coming classes. And so you can actually count things without actually literally listing them. What would you think for the next problem? How would you actually set that up? Because that one is a little bit more complicated now. Now we threw in the days of the week. How do you actually set that one up? One of the girls is born on a Monday. Yeah.
So the girl, like, she has to be in the first position, so one of them's a girl, right? Or it eliminates anyone, it's like 2 boys. And then there's 7 days in a week. So there's 7 variations of those.
Okay. So how would you visualize this situation?
There's 3 coordinates in
3 coordinates.
each back.
How would you set up these coordinates?
The same as the first 2, the same as the previous one, so the girl, boy, and the last one is David.
So here, let's sex of first child. Sex of second child. What do you put in the third coordinate? Day of what?
Like standard 7-day week.
Yeah, but what does this day signify in this
Oh,
situation?
day of birth. Gotcha.
Day of birth for who?
Second child?
Second child.
So the day of birth for the first child doesn't matter?
Oh.
I would actually think of this as 4. Let's do the day of birth of the first child and day of birth of the second child. Now, one thing we do know is that there's an M in this location. That's the only thing we know for sure. So now we just have to figure out what is the total number of possibilities with an M in that location, right? So the others can change. This could be boy or girl, this could be boy or girl, and this could be Monday, Tuesday, Wednesday, Thursday, or Friday. So there are Saturday, yes, people get born on the weekends, or Sunday. So there are 7 possibilities in this situation. There are 2 in here and 2 in here. How did we, what else were we told?
Oh yeah, so the first one's a girl.
We don't know who was born on the Monday. So we could have, if we put a Monday here, this is the date of the first child, that means we're assuming there's a G here. Or the other situation is, there's a G here and an M here, and that's where we don't know boy or girl, and this way we don't know Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So basically, if I were to count all of these possibilities, and then count all of those possibilities, and then add them up, I will get the total number of possibilities. And
the other.
the M should be over here, yes. And here's Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. But we know that there's an M in this location.
B or G.
So now we have to come up with a way to count these coordinates that have a certain pattern that goes with them, right? And that's what's going to kind of lead us into the next class. We're going to, well, the next class after tomorrow's class. We're going to start to do that. We're going to look at a situation, we're going to know, do I want to think of this in terms of sets or tuples? And then once I make that choice, how do I actually count all these possibilities? I mean, it's already starting to get pretty complicated here. And we will stop there. So this isn't on the test tomorrow, it's just everything we covered up the last time.
We got,
What?
so, 2 minutes?
Oh, today I'm available 12 to 2 if you want to stop by. Starting 2:30, I'm going to have like back to
Yeah, I'm gonna go.
Sure.